Hey guys, it's Miss Johnson and I'm here to bring you our notes video for Chapter 9. We're in the first section of Chapter 9, Section 9.1. Bear with me here because I think we're going to get through this whole section in one video instead of two. So just heads up on that. So we move into hypothesis testing, significance testing in this chapter. So we are going to leave confidence intervals behind for a while and do significance tests of proportions instead. The good news is that the layout of a significance test is pretty similar to the layout of a confidence interval. We just have a different formula to follow, basically. So confidence intervals are one of the most two common methods of a statistical inference. The other common method is a significance test. So this significance test allows us to weigh the evidence in favor or against a particular claim. So a significance test, or sometimes it's called a hypothesis test, is a formal procedure for using observed data to decide between two competing claims called the hypotheses. The claims are usually statements like about the parameter, like a population proportion or a population mean. So when we state the claim, it says the claim that we weigh evidence against in the significance test is called the null hypothesis, or H sub 0. The claim that we are trying to find evidence for is the alternative hypothesis. So here's just an example. It says a free throw shooter claims that his long run proportion of made free throws is 0.8. But we suspect that the player is exaggerating. Usually the null hypothesis, H sub 0, is the statement of no difference. And then the alternative hypothesis is what we believe may be inaccurate about the null, or could be inaccurate about the null. Here's one thing that I want to point out. Notice that these two numbers are the same. That will always be true. Always the same. Okay, so your null hypothesis, your H sub 0, is whatever the claim is. Okay, the statement of no difference. Whatever the claim is, that's your null. The alternative, so that H sub A, your alternative, is going to have an inequality symbol. You're either going to be less than or greater than, or just unequal to. So that's typically what happens there. That's the only thing that changes in these two statements. You've got the null, which is an equal sign, and the alternative, which is going to be some sort of inequality symbol. So the alternative hypothesis is one-sided if it states that the parameter is greater than or less than. It's a two-sided test if you're stating that it's unequal, okay? So one-sided meaning I think it's above or below. Two-sided meaning I think it's not equal to this, meaning it could be above or below. So that's why we call it two-sided. So let's just practice stating a hypothesis here. It says that the Hawaii Pineapple Company managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wonder if this change will affect the mean weight of pineapples grown in the field this year. State the appropriate hypotheses for performing a significance test. Be sure to define the parameter of the test. So that's one thing that's important. You have to define the parameter. You're looking at mean, and you're looking at the mean of pineapples, mean weight of pineapples, and it is the mean in ounces. So when we state the parameter, when we state the hypotheses, our hypothesis will look like this. Our null hypothesis is going to be that mean is equal to 31 ounces. And then the alternative hypothesis, it says managers wonder if this change will affect the mean weight of pineapples. Affect. They don't say whether it's greater than or less than, they just say it will affect them. So our alternative is that the mean is not 31 ounces. So does that irrigation system make them larger? Does it make them smaller? We don't know. All it says is, will it affect them? And then the other piece to this is that we have to state what the parameter actually is. So where we would say where mu is the true mean weight of pineapples grown in this large field, And then I should also say in ounces. You probably could have said the true mean weight in ounces grown in the field this year, because they're specifically referencing this year. So this is my hypothesis, and this is what is the parameter. Okay, those are the two pieces. That's going to be part of your state when you do your statement. Okay, so here's your caution. It says the hypotheses should express the belief or suspicion we have before we see the data. We want to state this at the beginning, before we start doing calculations. Hypotheses always refer to a population, not a sample. So your hypothesis should not, it says it is never correct to write a hypothesis about a sample statistic such as p hat or x bar. We want to do p and mu. Okay, so be careful there. Your hypotheses, just like when you would state what you're finding for the confidence interval, you'd state it in terms of the parameter. But then when you actually found the confidence interval, you're looking at the statistics. All right, so let's talk about p-values. So a player who claimed to make 80% of his free throws made only 32 out of 50, which is 0.64 in a random sample of 50 throws. This is evidence against the null, that p equals 0.0, and in favor of the alternative that p is less than 0.80. But is the evidence convincing? That's the piece. So we know that we have evidence that the player shoots less than 80%, but is it convincing enough? So it says, in other words, how likely is it for an 80% shooter to make 64% or less by chance alone in a random sample of 50 attempts? So if we repeat this 50 times, if we repeat this 400 times, we repeat 50 shots 400 times, how many times did we get 0.64 or less? Down here, they got it 3 times. So is that convincing enough? Is that convincing enough? Is that unlikely enough for us to say, yeah, if this was truly the mean proportion, then we should not have gotten this sample statistic. So then that tells me that the mean is inaccurate. So that's what a significance test is going to do. We're going to look at how unlikely is it for us to get the sample that we did. If it's really unlikely for us to get the sample that we did, then that suggests that our original hypothesis, our null hypothesis, may be wrong. So the p-value of a test is a probability of getting evidence for the alternative hypothesis as strong or stronger than the observed evidence when the null hypothesis is true. So in this case, 3 out of 400 is 0.0075. So what does this number mean to me? This is going to be an important number for you to look at, okay? When we tested this, knowing that the 80% was true, we only got 64% 3 times out of 400. That's a really low probability. That's pretty convincing to us, okay? Look at all of these ones that are up higher, and these just baby little 3 down here that are low. So this number right here is going to be something for us to focus on, so hang tight to that. All right, so let's interpret the p-values. It says, calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommends a calcium intake of 1,300 milligrams per day for teenagers. The National Institute of the NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decide to perform a test. So here's the null. Mean should be 1,300. Alternative, teenagers are getting less. Okay, null hypothesis, alternative hypothesis, and here's them stating the parameter, okay, where mu is the true mean daily calcium intake in the population of teenagers. So in your full hypothesis testing, this would be the statement part, okay? They ask a random sample of 20 teens to record their food and drink consumption for 1 day. The researchers then compute the calcium intake for each student. Data analysis reveals that the mean, the X bar, the sample mean, is 1,198 milligrams. and the sample standard deviation is 411 milligrams. Researchers perform a significance test to obtain a p-value of 0.1404. Explain what it would mean for the null hypothesis to be true in this setting, and then interpret the p-value. Okay, so explain what it would mean for the null hypothesis to be true. If H sub 0 is true, then the mean daily intake of calcium in teenagers is the 1,300 milligrams. Okay, that's what the null is saying. The null is saying that our mean daily intake is 1,300 milligrams, okay? Now let's talk about this p-value, okay? So this p-value is 0.1404, okay? So 14% roughly. Interpret the p-value. So I erased my screen to give myself some room to write here. But if we assume that this mean is true, so assuming that the mean is true, there is a 0.1404 probability of getting a sample mean of 1,198 milligrams or less by chance alone. And then you always need to state the sample size. In a sample of 20 teens. Okay, so this piece right here is kind of looking like what your conclude statement will look like. So we'll talk more about, again, when we go from confidence intervals to significance tests, we're still going to go through that state, plan, do, conclude process. This is kind of what your concluding process will look like, except that we're going to test against an alpha level, which we will talk about soon. Okay, so making conclusions. It says we make a decision based on the strength of the evidence in favor of the alternative hypothesis and against the null hypothesis as measured by the p-value. So we have to calculate that p-value, and then we have to conclude if it's enough for us to decide against the null. So if the observed result is unlikely to occur by chance alone, when the null is true, or in other words, you get a really small p-value, then we reject the null. If the observed result is not unlikely to occur, or in other words, you get a larger p-value or like a reasonable p-value that doesn't surprise you, then we fail to reject the null. I want you to look at that language right there. Reject and fail to reject, okay? We always want to talk in terms of the null. We never say accept the alternative. We don't ever want to say that. We always talk in terms of the null, because we're not actually going to test whether the alternative is true or not. We're really just testing against the null. And I know that's a really weird difference to think about, but that's what's happening here. We always want to talk in terms of the null. So how to make a conclusion in a significance test? If the p-value is small, we reject the null. And we conclude that there is convincing evidence for the alternative in context. If the p-value is not small, we fail to reject the null, and we conclude that there's not convincing evidence for the alternative. So how small does a p-value have to be for us to reject the null? Well, typically in chapter 4, we talked back about a boundary line of 5%. Typically we're looking at 5%. Just like in our confidence interval, we were more often than not, doing a 95% confidence interval that goes along the same lines as the 5% alpha level. Okay, it's going to be called an alpha level. Sometimes they do a different alpha level. Sometimes they use an alpha level of 0.01 or 0.1. You can decide whatever alpha level you want, but there's risks and benefits to going in either direction, just like we saw in confidence intervals. So here's what I keep referring to, alpha level. So this significance test, alpha, okay, that's the Greek letter A there. So the alpha is the value that we use as our boundary line for deciding whether an observed result is unlikely to happen by chance alone when the null hypothesis is true. So if the p-value is less than alpha, we say that the result is statistically significant at the alpha equaling whatever level, okay? And again, alpha needs to be stated before you do the data. So this is going to be part of your state as well, or maybe part of your plan. But either way, it's before you do the do part. Okay, so now let's talk about how that alpha level comes into play. So a company has developed a new deluxe AAA battery that is supposed to last longer than regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects a random sample of 15 deluxe AAA batteries and uses them continuously until they are completely drained. The sample mean lifetime is this. A significance test is performed using the hypothesis. So we want to test against the original data. Our null hypothesis is that mu is equal to 30. Our alternative is that mu is greater than 30. And we get this alternative by the sample mean. We're never going to change this value, okay? That value is going to be the same as the top value, the null hypothesis value. But the fact that our sample mean was greater, that's what decides our inequality symbol. So our sample mean was greater, so now I'm going to say my alternative is that the mean is greater than the null. Then notice where mu is the true mean lifetime in hours of deluxe AAA batteries, they state the parameter, that's important. Okay, the resulting p-value, so they did the calculations and they found a p-value of 0.0717. What conclusion would you make at the alpha 0.05 level? So if we were going to conclude something, I kind of think of this as a thermometer. So if I'm looking at this as a thermometer and my alpha level is 0.05, where does my p-value fall? Okay, if it falls below, it's kind of like those days where you would wait to see if you could go outside for recess or not. Is the thermometer going to be above 20 degrees or is it going to be below 20 degrees? Or I don't know what the temperature is. I don't know if it's 0. I don't know what it is. But you get what I'm saying. Am I falling above or am I falling below? If I am above, okay, this is where we are going to fail to reject. We have a high enough p-value to fail to reject the null in that case. If I fall below, that's where it's like danger, danger, too cold to go outside. If I fall below, this is where we're saying this is statistically significant. This is meaningful to us. We are going to reject our null here. Okay? If I fall below that alpha level, that's where red flags are raised. I'm going to reject the null because I have a significant enough value. It's so unlikely for this thing to happen if I'm falling below my alpha level. It's so unlikely for it to happen that I don't think my null hypothesis is actually true. I'm going to reject the null because I don't think it's actually true. So let's talk about it in context of this question. So in this question, here's our little measuring stick. And again, I draw this a lot. So here's my measuring stick. Here's my alpha value. My alpha is 0.05, okay? Alpha, by the way, means beginning in Greek. So that's like our starting point. That's our measuring stick. That's what we are sticking to for the starting point. That's why it's called alpha. So our alpha value here is 0.05. My p-value is 0.0717. I'm up here. Okay, so what does that mean? Well, up here, we fail to reject. It is not all that uncommon for a battery to last 33 hours. That's what they're saying. It's not all that uncommon. It happens 7% of the time. So if it happens 7% of the time, that's not enough for us to say that the null is true. Okay, we are going to fail to, or that the alternative is true. We're going to fail to reject the null because we think the null might actually be true, because it's not all that uncommon for us to get a battery life of 33 hours. So here's how I would write that out. Because P equals 0.0717 is greater than 0.05, which is my alpha, we fail to reject AO, or HO. Okay, when you're making a concluding statement, you have two sentences involved. There's your first sentence. Talk about it in terms of the data. Your second sentence, now put it in context. We do not have enough convincing evidence that the true mean lifetime, here's my context, I'm going to come down here, sorry, mean lifetime of the company's deluxe AAA batteries is greater than 30 hours. Okay, sorry, I kind of wrote around the box here. Hopefully you can see all of that. So again, two sentences. The first sentence gives us the data, this piece right here. Then the second sentence gives us the context, that second piece right there. Here's your caution. We never want to write accepting HO or that HO is true. We fail to reject because we don't actually know if HO is true. We're just failing to reject it at this time. Okay, we recommend that you here's your two sentences. Look at that, I was ahead of myself. We recommend that you follow the two-sentence structure from the example when writing the conclusion for the significance test. The first sentence should give a decision about the null hypothesis based on the explicit comparison of the p-value to the significance level, okay? This is like your data calculations. Then the second sentence should provide a statement about whether or not there's convincing evidence for HA in the context of the problem. Okay, this is like your context. Those are your two sentences that you need. This right here is the conclude portion of your significance test. So far we've talked about the state and we've talked about the conclude. Now we're going to get into the plan and the do. Before we do that, we have to talk about errors here because it is possible for us to make a mistake. It is possible for errors to happen. When we draw a conclusion from a significance test, we hope our conclusion will be correct, but sometimes it's wrong. There are two different types of errors. A type 1 error occurs if the test rejects the null when the null is true. That is, the test finds convincing evidence that HA is true when it really isn't. Okay, so type 1 error means that we had a low p-value, okay, when we shouldn't. This is kind of how I remember these, okay? A type 2 error, here's a type 2 error. If the test fails to reject, so we fail to reject, so our p-value is high, but it shouldn't have been. That is, the test does not find convincing evidence that H sub A is true when it really is. So type 2 error was a high p-value when it shouldn't have been. So type 1 error is low. Type 2 error is high, when both of them when they shouldn't be. Okay, that's kind of how I remember that. Okay, let's talk about these errors. It says a potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load of potatoes from the supplier. Otherwise, the entire truckload will be used to make potato chips. To make a decision, a supervisor will inspect a random sample of 500 potatoes. The producer will then perform a significance test with an alpha value of 0.05. Here's your null and alternative. The null is that the proportion is 0.08. The alternative is that the proportion is greater than 0.08, where P is the true proportion of potato blemishes in a given truckload. There's your parameter. Okay, so there's your hypotheses. And then there's your parameter. Describe what a type 1 error and type 2 error in this setting would be. And then they also say, describe a possible consequence of each. So type 1 error, again, type 1 error is that it's low when it shouldn't be. So type 1 error is that the producer finds convincing evidence convincing, I can't write today, you guys, convincing evidence that more than 8% of the potatoes have blemishes. When they really didn't. And what would the consequence be here? They'd send the truck away when they could have used them. Sad panda. That's a lot of sad potatoes. When they could have used them. Okay, that's your type 1 error. So they found convincing evidence, but they shouldn't have found convincing evidence because the truck was actually okay. If they do that, they're going to send the truck away, not use the potatoes, wait for another shipment, delays everything, waste of resources, waste of the truck driver's time, waste of the, product. Now you've got all these potatoes that somebody's not going to use. Huge production problem here, okay? So now type 2 error, let's talk about a type 2 error. Type 2 error. Okay, type 2 error would be that the producer does not find convincing evidence. So remember, type 2 error is high p-value. High p-value means that you fail to reject the null in favor of the alternative and accept whatever the null is. So the producer fails to find convincing evidence. The producer does not. That more than 8% have blemishes when he should have. So what's the consequence here? The consequence here is he uses the potatoes when there's more that have blemishes. So he uses an unacceptable batch of potatoes. Potatoes, I didn't mean to put an E there, sorry. I needed an E there. He shouldn't have causing lower quality chips and unhappy customers. Okay, so rejecting the null when you shouldn't sends the truck away, a waste of time and resources. Failing to reject the null when you should, using a product that you maybe shouldn't be using, and then creating something that has lower quality. That's what's happening with these two errors here. Okay, so type 1 and type 2 errors, it says the most significant alpha levels are these three, this one being the most significance, but then 0.01 and 0.1 are ones we use as well. Which one of these is the best choice for a given significance test? Well, that depends on which error is more damaging to you. So it depends on whether a type 2 error or type 1 error or type 2 error is more serious. The probability of making a type 1 error in a significance test is equal to the significance level. So if you want to have a lower type 1 error, that means you need to have a lower alpha level. Okay? Lower type 1 error means lower alpha level. Lower alpha level means it's harder to reject the null, because you have less area in your little thermometer. You know, if your alpha level here, I don't write alpha very well, alpha level here is 0.05, you have all this space underneath to reject the null. But if your alpha level is 0.01, you have way less space to reject the null. You just don't have very much room to reject the null. So take that for what it's worth. If it's not too bad for you to make your type 2 error is up here when you have too high of an alpha level. So if it's not so bad for you to make a type 2 error, then reduce your alpha level. If it's worse for you to make a type 1 error, reduce your alpha level. But if the type 2 error is more damaging, then you need to increase your alpha level. But then you have more of a chance of making a type 1 error. It's all give and take. When I said that people can manipulate statistics however they want, I was not lying. All right, so here's just that kind of in a nutshell. We can decrease the probability of making a type 1 error in a significance test by using a smaller significance level. But there's a trade-off between type 1 error and type 2 error. As one increases, the other decreases. That's an ebb and flow. If you lower your significance value, you have more probability of making a type 2 error. So if we make it more difficult to reject the null by increasing or by decreasing alpha, we increase the probability that we will not find convincing evidence for the alternative when it is true. So if you lower your type 1 error, your type 2 error goes up. All right, that's the end of our section for 9.1. So hopefully you made it through this video. Thanks for listening. In 9.2, we're actually going to carry these significance tests out all the way through. We've only talked about them in little pieces in 9.1. So heads up on 9.2, we'll actually do the whole thing from start to finish. So thanks for tuning in, and I will catch you next time.